So today's presentation, kindly provided by Dr. Richard Garrett, is on the hunt for dark matter at the Stawell Underground Physics Laboratory. And I'll just introduce Dr. Richard Garrett. So Dr. Richard Garrett has over 30 years of postdoctoral experience working at major synchrotron facilities in the United States and Japan, in addition to the Australian synchrotron. So Richard was the facility director of the Australian Synchrotron Research Program until 2009. He has provided expert technical advice to the Australian Synchrotron in a number of capacities and as a key figure in ANSTO's role as an operator and now owner of the facility. At the time of his retirement in June 2023, Richard served as a senior advisor, strategic projects at ANSTO, where he played a lead role in ANSTO's relationships with several national and international programs and organizations. Richard holds an honorary associate professor appointment at the ANU. Richard was recently appointed the science director of Stawell Underground Physics Laboratory, which will host the first direct detection of dark matter experiment in the Southern Hemisphere. So thanks very much, Richard, for agreeing to give us a talk today. I'll hand it over to you.
Thanks very much, Mark, and very pleased to be able to present our work down in Stawell in Victoria. If you ever meet someone from Stawell, don't call it Stawell. It's Stawell, like stall your car. So
thanks.
Let me find my share the screen. So can you see that? Do I have the correct view?
No, you're still on presenter view. That's good now. That's good now.
Okay.
Except we've got a bit in the middle.
You can see that okay?
Yep. That's good.
Okay. So yes, I'm going to describe the role that the Stawell Underground Physics Laboratory, which is recently completed in country Victoria, is hopefully going to play in the hunt for dark matter. First of all, I'd like to present the mystery of dark matter and the dark universe in general. So really, these are two of the great mysteries of modern science. What makes up 95% of the universe, whose effects we can see, but which we cannot directly see. I'm not going to spend any time on dark energy because I think it's even less understood than dark matter. But I am going to concentrate on this green segment of the pie chart, dark matter, which makes up about 85% of the mass of the universe. So ordinary matter, you and me, the world, the sun, the stars, are 5% of the universe as far as we can tell. So how do we know that this is the case? And primarily, the evidence we have is observational evidence from astronomy. And this picture here of the Abell cluster taken by the Hubble Space Telescope is one of my favorite pieces of this evidence. You can see, if you look closely, there's these little streaks on this photo, which looks like you've scratched the photographic plate or something, but in fact is, of course, not taken on a photographic plate. These streaks are distorted images of galaxies behind this cluster. And what's happening is that the mass of this galactic cluster, which is enormous, over 100,000 galaxies in this cluster, is bending the light from distant galaxies around the cluster to where we receive it at Earth, and therefore distorting the images of these very far galaxies. So it's it's relatively easy to calculate the total visible mass of this cluster. And when you do that, you find you need about 20 times more mass than is visible to create this lensing effect, this gravitational bend of the images of the galaxies behind. So typically, and as is the case with all these dark matter issues, it's not a matter of we're missing 10% of the mass of the universe. We're missing 85%, huge amounts. And it's possible to calculate the distribution of dark matter in this cluster due to those distorted images from the galaxies behind, and that's what they come up with, this map of dark matter within this cluster. Another very commonly seen piece of evidence, and I think Virginia Kilbourne showed this last year at the conference, is the rotation of galaxies. If you think of our solar system, the further you get from the sun, the slower things rotate, because the force of gravity from the sun gets weaker and weaker. But this does not occur with galaxies. And you can see this dotted line here is what you would expect the rotation speed of the galaxy out to the spiral arms from the visible matter in the galaxy. But what we actually measure is this other curve where the rotation speed of the galaxy is almost flat, and that actually, in fact, increases a little bit. And this is due to the fact that all galaxies, we believe, are surrounded by this halo of dark matter, which extends much further than the radius of the actual normal matter of the galaxy, something like this. So every galaxy is embedded in this halo, so-called, of dark matter, which is responsible then for this unusual rotational profile. And just remember this point, because this comes back to an important aspect of the measurement attempts to discover dark matter. So every galaxy, including our own, is embedded in and rotating within this halo of more or less stationary dark matter. Where did this all come from? Well, this is our sort of standard picture of the history of the universe. And what is expected, what is proposed is that dark matter, you can see if you squint here, was formed at the very beginning of the Big Bang, along with all the other elementary particles. It's 10 to the minus 10 seconds of the Big Bang. And as the universe has expanded and the standard model particles are formed and nuclei are formed and atoms are formed, eventually we get to the formation of something like the universe as we know it, with stars and galaxies. But all the models say that the force of gravity is too weak to form stars and galaxies by just the attraction of hydrogen atoms, because not only is that a very weak force, but there's a lot of radiation even here, which is scatters the hydrogen atoms to the effect that you would not have enough force to form galaxies and stars. However, dark matter is not affected by radiation. It's dark. So it was able to form clumps and therefore form galaxies and stars due to its gravitational attraction, and hence those halos around the galaxies which survive even to today. So what is this missing matter? There's been a lot of work done. Most of the obvious candidates have been eliminated because there's either not enough mass or there's just not enough of them, such as black holes, which we clearly mostly can't see, and other massive objects. Very dim stars like brown dwarf stars that have ended their life, interstellar dust, neutrinos, of which there's a lot but not enough, etc. And what remains is either our theory of gravity is wrong. So maybe on these very large scales and very large mass scales, gravity is functioning differently to what general relativity tells us. This, in principle, is possible, but thought unlikely at the moment. No one's come up with a new model of gravity that explains all the observational evidence. So what we're left with are hard to detect particles. So what could they be? Here's the standard model of foundational physics. All the elementary particles that we know of, the quarks, the leptons, the electrons, muons, neutrinos, and the bosons, the force particles, and photon. So we know quite a bit about all these particles, and this model, the standard model, has really withstood almost every test that's been thrown at it for the last probably 30 years, more or less. However, we know it's not complete. If a unified model of everything has to include gravity, which the standard model doesn't. It unifies the other three forces, electromagnetism and the strong and weak nuclear forces. It doesn't explain why there's way more normal matter versus antimatter in the universe. And it doesn't explain dark matter, because what we know of dark matter, you can see down the right-hand side here, are 4 characteristics. We know it's stable. It's survived from the beginning of the universe. We know it interacts gravitationally because that's the effect we see. We know it's cold, so not relativistic, because these halos still survive in place around galaxies. And we know it's dark. It doesn't interact with light, the electromagnetic force, hence dark. And that wipes out every particle in the standard model. They're either not stable, they're not dark, they don't in fact interact gravitationally, or they're relativistic like neutrinos. And some of those particles would have more than one color cross against them. So what we're left with is a new particle beyond the standard model. We're also left with a huge challenge, because we really don't know much about this particle aside from seeing its gravitational effects. So in principle, it could be anywhere in an enormous mass range, as shown here. And then we come to our Center of Excellence for Dark Matter Particle Physics. And this center is concentrating on 2 of the most promising candidates for dark matter. One of these axions, also in a class called WISPs, which are weakly interacting sub-EV particles. So see here on the energy scale is 1 EV. So somewhere in this region are these proposed particles, and axions are one of the most promising candidates there. On the other end of the mass or energy scale are WIMPs, weakly interacting massive particles. And that's probably the most promising candidate for dark matter, and the one that's been searched for by quite a number of experiments around the world. So these are the 2 main arms of the Center of Excellence. But if you look around and just consult Wikipedia, you find a much more complex picture of this enormous number of particles that are being proposed by various researchers to explain our missing mass. Anyway, from here, I'm going to concentrate on WIMPs, because that is the particle that we propose to search for in the Stawell Underground Physics Laboratory. So how do you go about detecting something like this? Well, we have issues with detecting very hard to detect particles, especially on the surface. If you look on the left-hand side, you see a calculation of the cosmic ray background at the surface of the world, of the Earth. Billions per square centimeter arriving every day. And on the other hand, we've calculated if a WIMP is in the mass range that we saw there, that there'd be something like 1 billion a day passing through that same kind of area. Now, WIMPs, of course, will pass straight through the Earth, whereas in general, only cosmic rays can be shielded. So if you go underground, you get away from this issue of the WIMPs. You might get one event per 10 kilograms of detector per day, if you're lucky. Whereas on the surface, you'll get over 1 million events from cosmic ray background. So going underground is essential, and all the experiments that are in place around the world are all in underground laboratories of the order of 1 kilometer or more underground. And this just shows this again. Here's a fairly standard photo on the left, image on the left of a cosmic ray shower. You can see you get this cascade of all kinds of particles produced by a very high energy cosmic ray. And as you go deeper, if you look at the graph here, you can see things are shielded off more progressively, and muons are basically the biggest surviving component as you get down to over 100 meters of water equivalent. The dotted line here is neutrinos, which are not shielded at all, but also probably won't be picked up by your detector, so not really an issue. And here on the right is a graph of many of the world's underground laboratories versus how deep they are. And to compensate for different geologies at the different labs, what people do is convert the overburden, the rock above the lab, into an equivalent depth in water. And then you get everything sits quite nicely on this line of the shielding of the muon flux progressively as you get deeper and deeper. And you can see our Stawell lab is right very close to Bulbi, which is in the United Kingdom, and the Gran Sasso lab in Italy, and the fact that we're close to Gran Sasso, as you'll see, is quite significant in our whole project. So how to detect a particle when you don't know anything about it is always a bit of a conundrum. And the consequence is that people are trying a very wide range of detectors to try to pick up dark matter. And they all rely basically on the direct collision of a dark matter particle, a WIMP, with the nucleus of a detector. And what is expected is that either some of the detectors are then sensitive to scintillation produced by the nuclear recoil. Some are sensitive to this tiny amount of heat deposited. Some are sensitive to ionization. So you see a whole range of different detector technologies. And in yellow are all the detectors that have been built using these technologies. And you can see there's a huge range of detectors, many of which are still functioning today, taking data. And all of them expecting of the order of 1 count per day. So yeah, not an easy process. But one thing helps us out a little bit, and that is we expect the signal to be modulated annually. So remember, our Milky Way galaxy is embedded in a halo of dark matter, and the sun, being on one of the outer arms of the Milky Way, is rotating around the galaxy at about 800,000 kilometers an hour. So it should be heading into this dark matter wind coming at us at that speed. And fortunately, the sun, our solar system, is inclined at an angle to the galactic plane. So you can see here the consequence of that is that in June, the northern summer, we are basically heading more into the wind. And in December, our southern hemisphere summer, we're heading away from the wind. Therefore, we expect any detector riding on the Earth to see more dark matter particles passing through it in June, July, than we would see in December, January. So this modulation would, in principle, help us pick out dark matter from the backgrounds even more. And in fact, the Dharma Libra experiment in Italy in the Gran Sasso Underground Laboratory sees exactly this modulation. And what you can see here is 3 runs of this detector, they've gradually improved signal to background. And over 20 years data where they see just this peak, a small peak in summer in the Northern Hemisphere and a lower in the winter months. Exactly what would be expected. And you can see this is a sodium iodide detector in the middle of a whole bunch of shielding, and then more than 1 kilometer underground. Great. And this result was greeted with a whole lot of excitement back 20 years ago, but unfortunately, no other detector has managed to reproduce this modulation. So, and I think it's fair to say that the operators of all these other detectors don't believe this result anymore. But basically, we're left with two possibilities. Either sodium is special, so the sodium iodide crystal is more sensitive to dark matter than, say, these liquid xenon detectors, or there is a seasonal background in the Italian lab that they haven't managed to exclude. Their claim is they've eliminated every possible source of error in their measurement, but who knows? And this, just a little aside, this is a sort of typical thing you see in these dark matter experiments. This is a graph of the nuclear cross-section. So the probability that your detector will pick up a dark matter particle versus the WIMP mass, which with this big range of over a factor of 1,000 in potential mass of WIMPs. And you can see here's the Dharma Libra areas of sensitivity. And a lot of these other detectors are pushing way lower and not seeing the modulation. So that on first sight doesn't look very promising, but maybe sodium is special. And at the bottom, you see the neutrino coherent scattering. You can't shield against neutrinos, and at some very low level, your detector will start picking them up. So that's like a no-go area for these experiments. So the proposal has been for some time to test between Italy and Australia with identical detectors. And this is a new generation sodium iodide detector, SABRE, which has an active background rejection, which we'll see. So the proposal is to install identical detectors in the Gran Sasso lab in Italy and in SUPL in Stawell. And therefore, with the Northern and Southern Hemisphere detector, if we see the same modulation, then that's pretty much confirming that the fact that the Dharma Libra experiment is detecting dark matter. If we see a seasonal variation out of phase, then they've messed up. And what they're seeing is a summer-winter variation, which just unfortunately aligns with the expected modulation of dark matter. So these detectors are improved in several aspects. There'll be higher purity crystals. As you'll see in the next slide, active scintillation veto liquid surrounding the whole detector to try to screen out any counts from either external or from any remaining radioactive isotopes in the detector itself, which is also a big issue. And here's what you see. We have sodium iodide crystals at the center of the detector, this big volume of scintillation liquid and more photomultipliers picking up events in the scintillation liquid to then gate off the detector. And I think this might be a little video. Yes, so there you can see the very, very transparent sodium iodide detector elements. And there's a little video of how dark matter is supposed to scatter off the sodium atom, which then causes a little flash, which is picked up in that detector element. So in principle, that's how it should function. Of course, maybe in your sodium iodide crystal, unfortunately, you have a little potassium atom sitting there, which is radioactive. So it would then give off electrons and flashes that would be picked up by all the detectors. So hopefully not not identified as dark matter. So I think that's probably enough of the video. So linear alkyl benzene is that huge scintillation liquid that's filling the whole detector. So then we come to the Stawell Underground Physics Laboratory. This project actually kicked off about 10 years ago when the rumors started flying around Stawell that the gold mine was going to close, and they started looking for what else could be done with a big hole in the ground. And some of the astrophysicists in the Swinburne University, Jeremy Mould in particular, got quite interested in the possibility of constructing a lab underground in the Stawell Gold Mine. And things sort of developed from there. You can see here is a refuge. That's a little chamber that is installed at various places around the mine for if there's a cave in or whatever, you get to the refuge and you've got enough air, etc., for many days for somebody to come rescue. And some initial experiments were done in this refuge, about 1 kilometre underground, back in 2015 or so. So the Stawell Underground Physics Lab kicked off after that. There's 5 collaborating partners. Melbourne University is the lead organisation, and then there are Swinburne, University of Adelaide, ANU, and ANSTO. And of course, the Stawell Gold Mine is a key partner as well, although not a research partner. About $10 million construction funding was granted from the Commonwealth and Victoria back in 2017 or so, and the lab construction began in 2019. And all the 5 partners are committed to fund the operation for the first 5 years. So there's Stawell. It's about 2 to 3 hour drive out of Melbourne. You go through lovely Ballarat on the way. There's it's a very nice little country town, so not a bad place to visit at all, although a bit chilly this time of year. So the gold mine is not what I first thought of as a mine where you get in an elevator shaft and have a ride down for a kilometre. It's a drift mine, which is the other kind of underground mine where you drive down on a road. And then the mining activity is built on side shafts out from the road, as you see here, and bits chasing the gold ore. So Stawell is a 1 kilometre down, which is about a 30 kilometre drive through these tunnels. On the one hand, this is a bit more difficult to take sensitive equipment down because the road, as you could imagine, is not exactly smooth as silk. On the other hand, you can go down almost any time. You don't have to wait for once or twice a day in the big mine elevator. You do have to dodge, as you can see here on the right. Here's a big ore truck coming out of the mine. And you can see it's a one-way road. So there's radio contact every time people are driving up and down, and little turnouts where they can wait for ore trucks to go past them. And again, here's the equivalent position of SUPL, our underground lab, compared to some of the other laboratories in the world. And in particular, very close to the Grand Sasso lab, which is going to have our Northern Hemisphere SABRE detector. Construction took place mostly 2020 to 2022, really nicely aligned with COVID, which held things up a fair bit. One of the things ANSTO did was establish this temporary underground materials testing laboratory at 729 meters below the surface, where we installed a small sodium iodide detector. And we used that detector to measure all the components of the mostly concrete that went into construction of the laboratory. You can see on the right here, the cavern is being excavated, and what was done was concrete, shotcrete was sprayed on all the walls and ceilings to stabilize the whole cavern. And then after this photo, the floor was laid. So this was many, many tons of sand, aggregate, cement coming to Stawell. And it was sourced from all around the country to identify the lowest background component for all these sands, aggregates, and cements. So cement came from Queensland, aggregate came from South Australia, and sand was sourced locally, fortunately. And here at the bottom is the laboratory completed in 2022. And I was lucky enough to be able to go on a drive down and be present at the opening. So 2022 construction was complete. There's the main experimental hall. We have a couple of enclosed rooms which are initially designed for installation of high purity germanium, very ultra low level detector laboratories. And the environmental conditions are there. And what that tells you, if you ever go down this mine, you'll find out that the temperature outside is about 32, 35 degrees, and the humidity is 90% or so. So we have a fairly serious air handling system to reduce our temperature to 22 and our humidity down, etc. And our goal is less than 100 becquerels per cubic meter of radon. More of that soon. So here's a floor plan of the laboratory. This is the so-called drift. So this is the road down, which goes around the corner here. So equipment entry is via this truck loading bay, and personnel entry is via this area here, where you can go in, you can get changed out of your dirty overalls you rode down in the truck. You can shower in, and there's a control room area in here. I hope you can see my pointer. The SABRE dark matter detector will be installed in the main experimental hall. And there are these two enclosed laboratories, 50 square meters of space. It's all equipped with power, gases, liquid nitrogen will be provided soon. And as it says here, the design allows for future expansion in either direction behind here by excavating yet more rock. So the laboratory is there, it's fitted out, it's ready to go. And so what are our next steps? The first thing we need, one of the first things we need to do is reduce our radon level in the laboratory. So ventilation in the Stawell Gold Mine is basically air pumped down the drift. So it goes down 30 kilometers of tunnel and therefore naturally picks up whatever radon is naturally in the mine, which is too high for what we want to do for a lot of these experiments. So we're looking at a lot of options. There's the potential for piping down surface air. This already is delivered to those refuges, for example, to allow people to survive in the case of some accident. The dark matter experiment. The dark matter experiment is due to be installed next year. I think someone's not muted. And basically, it needs to run for 3 or 4 years to measure several, hopefully, periods of this oscillation in concert with the Northern Hemisphere detector to conclusively either prove or disprove the Dharma Libre result. But a lot of other experiments are possible underground. In particular, nearly every underground lab around the world runs an ultra-low-level metrology laboratory. So one or several high-purity germanium detectors looking for very low-level, measuring very low-level radiation samples, either samples for other astrophysics detectors, for example, or environmental samples. at ANSTO, they measure a lot of environmental samples looking at as isotope traces, looking at things like some of the bomb atmospheric testing isotopes like cesium, etc. And these are fading out as time goes by. So at some point they would need something like SUPL to reduce their the background and increase the sensitivity of the measurements. Quantum has become quite an interesting area of possible need for underground labs. Some of the quantum computing technologies, especially the ones that are superconducting, so running at extremely low temperature, are susceptible to cosmic rays. So if a cosmic ray hits your qubit, it's going to break the coherence, and that's maybe the limiting factor on the coherence time of a lot of these quantum computers. Still to be determined. Similarly, people are just starting to realize that the material you make your quantum system out of is going to have some level of radioactive isotopes, and screening for these materials is also potentially quite something that would need an underground lab for that level of radiation metrology. There are some initial proposals to conduct radiation biology experiments in the lab. As I'm sure we're all aware, a lot of our radiation safety is based on the linear no threshold model, but it's becoming pretty apparent that that doesn't work at very low levels. And in fact, there's some evidence that very low levels of background radiation could actually be not harmful to bioorganisms. The future astrophysics experiments are planned. A particular one is the Cygnus directional dark matter detector that is being developed primarily at ANU. It's part of the Center of Excellence also. If you remember back to that cross-section diagram, the neutrino background at the bottom, which basically puts a limit on the performance of all these detectors, is primarily solar neutrinos. So if you have a directional dark matter detector, you can start discriminating against solar neutrinos and increase the sensitivity by reducing your sensitivity to neutrinos. And there's also some potential uses of the lab that don't rely on the fact that it's a low radiation environment, but that it's an underground laboratory in a working mine. And there's a lot of developments on sensors and artificial intelligence for remote operation of mining activities. And having a laboratory with the control systems, etc., in place in a mine is probably can generate some business for SUPL. So I'm going to leave it there. The last slide is just some acknowledgements, especially Elisabetta and Greg, who Elisabetta is the director of the Center of Excellence. I stole a lot of slides from both these people. Thank them very much. And the SABRE South detector experiment is run out of the Center of Excellence for Dark Matter Particle Physics. And you can see there are the top row are the university members of that centre. There are two Australian partner institutions, ANSTO and DSTG in Australia, and a range there of international partner organisations. So I think I'll leave it at that. Thank you very much for your attention, and over back to you, Mark.
Yes, thanks very much.
I'm happy to take questions, of course.
Yeah, thanks very much. Call you a professor because you are honorary professor, associate professor. So Professor Garrett, for that very intriguing talk. It certainly kind of opens up more questions, and there are real answers, especially this question of what dark matter is. So I'd just like to open the floor now to questions. So anyone that with a good questions, just type it in over the Q&A or just maybe raise your hands so we can put you off mute and you can ask your question. But maybe to kick it off, I've got a question of my own. What do you think, given, you know, you're lining everything up, when do you really expect, you know, first answers to come, and what would be the implications in terms of developing new theories as to what this elusive particle might be, WIMPs or WISPs?
Yes. So yeah, I should mention that the centre are also looking for the WISPs in primarily in the University of Western Australia, where the advantage of those is they're not sensitive to cosmic ray background. They searching for evidence of those in very low temperature experiments. But as far as SABRE and WIMPs are concerned, it's if we can get the detector down and operating next year, I mean, a year should tell us there's some variation or not to begin with. And then to really nail it down is going to take probably 3 years of measuring the modulation. But there'll probably be hints earlier than that. And I think the identification of at least the mass of a WIMP, even though we only detect its effect on the detector, and but that will be a very important step. It gives the theorists something actually real to start working on, rather than basically at the moment this wide open field of, well, it could be almost anything, so go for it.
Yeah,
I mean, supersymmetry was one of the big theories that did allow for a WIMP, and it actually was in a very nice energy range, so therefore was called the WIMP miracle. But supersymmetry has its own issues. So
perhaps I can just ask a question, Richard. Your timeline. The timeline. Are you saying you have the detector about to be installed, or
the detector is in pieces, but most of the pieces are here. The whole tank is fabricated. The shielding is fabricated. The scintillation liquid is sitting in a big tank at Stawell, ready to be taken down to the laboratory. The crystals are now being checked to make sure they are as pure and radiation quiet as we hope. So yeah, it's assembly of the detector is about to get underway. I would say probably late this year, early next year.
Right. We haven't got anyone else asking questions on the with the hand up. Perhaps talking a bit more about this technology. I mean, this system is very much dependent just as it's an interaction with a sodium.
Yes.
Atoms, sodium nuclei, is it?
That's right. So it's basically a direct scatter of a dark matter particle off a sodium nucleus is and you know, maybe given that you don't know exactly what dark matter is, or at all what dark matter particles are, does that even work? But that's the theories would tell you that yes, even a non-standard model, non-interacting dark matter particle should, with a very low cross section, be able to scatter off a nucleus. So yeah, then you get, how do you reduce all the other possible sources of scattering?
That's really interesting. So then the question, of course, is that if we're not certain about much, doesn't it mean that maybe you kind of need to just kind of go through the periodic tables, just try everything? Because if you don't know what you don't know, then the only thing you do know are stuff that it could possibly interact with these things.
That's right. And if you remember this slide, basically that's what's happening. A lot of different elemental detectors based on different elements are in place at various different laboratories. So yeah, there's a few bets being made around.
Is there a running bet as to like whether you're going to get a positive, you know,
I don't
output
know.
or
I
signal?
mean, yes, the Italians are still very confident in their result, and everyone not directly connected to that detector, I think, is quite skeptical. I think would be a fair characterization. But you know, this is the test. If the Southern Hemisphere sees the same modulation, then we really have something.
Well, I mean, at least there's facilities there, right? And you can
Yes.
just put more and more experiments in there.
Yeah. And if you look around the world at these underground labs, there are multiple experiments in all of them, and quite a range of different activities going on. So, I mean, we now need to get proper operating funding, hopefully from NCRIS in when the next roadmap comes around. I think 2026.
Wow.
But,
I mean, if it's something as fundamental as dark matter, you know, answering the question as to what is the fundamental
yeah,
nature of reality.
exactly. And you know, to be fair, the AIC funded the Centre of Excellence, so
Yeah, fair enough.
it's not totally impossible that we'll get some actual operating funding for the laboratory. The other, and actually another thing that people usually assume when I tell them about this project is that the gold mine is shut down. But that's, in fact, as I was saying, not the case. It's a very active gold mine. And in fact, if it was shut down, I don't think there's any way we could afford to run the laboratory. We'd have to provide our own safety, our own ventilation, power, internet, you name it. It probably cost 3 or 4 times what it's costing us to operate.
Don't see
What about the issue of vibration? If you're operating it in a
Yeah,
a few explosions, I guess.
There are explosions. Fortunately, they're not mining that close to us at the moment. They're chasing gold, although they are apparently working back a little bit in our direction. But they blast at very specific times in the day, and in fact, everyone has to evacuate the mine when blasting takes place. So we can definitely gate everything off during the blast, and we've had vibration monitors down there, and it's really not bad. It's the truck going past is worse.
All right. Well, once again, thanks very much, Dr. Richard Garrett. That was really interesting.